So that's when you have the pressure of the O2 is greater than the pressure of the atmosphere. What do you think it looks like when it's the opposite? The arms are opposite, right? I'll give you a second if you're right in there. The arms are opposite, then instead of adding that change in height, what do you think you should do? Subtract that change in height. Because you'll want to be subtracting it because there's pressure, the oxygen is weaker. My stopper again, it's connected. Here the oxygen, pressure of the atmosphere is pushing down. Give me an example. What do you want the height difference to be? 70? Okay, so who's going to be higher, the left side or the right side of the U-tube? The right side's going to be higher, so I'm going to put that way up here. That one way down there. So you can tell that the pressure of the atmosphere is pushing quite a bit. It's pushing so much that it made the water, or the mercury level, rise way far this side. So the difference here is from here to here is our delta H. Oops. That delta H we said was 70 millimeters of mercury. So if the normal atmospheric pressure is 760, how do you get to this pressure of the oxygen? So you're taking 760 millimeters of mercury, and you just told me the pressure of the oxygen was less. So it's got to be less than this, so you have to subtract 70 millimeters of mercury to give us what? 690 millimeters of mercury. Yeah.
Do you want us to convert the millimeters?
It depends on if the question asks for it, but usually I open you up to whatever pressure unit you want, unless we're using the ideal gas law, which we'll go later. You can convert if you want. It just takes extra steps, yeah.
So if it's more, you always add it. If it's less, you always subtract it.
Yes. And that makes sense with your pressure differences, right? These other ones, you're going to do a lab where you use a graduated cylinder as a measuring device. So the graduated cylinder is a way that you can measure the pressure of the atmosphere. In this one, where do you think it pushes? If this is a graduated cylinder. Do you notice it's upside down? So it's just turned upside down. There's still graduations on here. And then there's water in a beaker, and you got the, like the plastic part of your graduated cylinder up here. Where do you think the pressure of the atmosphere is pushing? Where? On the beaker? Or on the graduated cylinder? There's gas. This pink stuff is gas. This time it's gas, sorry. How about the pressure of the atmosphere pushes on the water right here and right here? If it's pushing on the water, where is the only place the water can go? Up where? Into the tube, right? So the water can actually travel up through the graduated cylinder if you have enough pressure difference. But in this case, notice the gas level is below the surface of the water. So who's pushing harder? If this pink stuff is still oxygen gas. The oxygen gas is pushing so hard that it's actually pushing the water out of its way. It's pushing down on the water, and it's displacing the water from that little part that's underwater. So, how much more is it pushing? Whatever this right here is, delta H. That's how you do this one. It just looks a little different because you have to say pressure of the O2 plus the delta H, pressure of the atmosphere plus the pressure of the OH. The delta H to give you pressure of O2. It's just that little bitty H this time. We'll work with these some more. It's just a fancy way of showing you pressure differences. When we do a lab, you'll have to make sure you know how to measure pressures with that one. Alright, this is the one I actually want to get to. Solving problems. Alright, so write down your givens here. And I want you to always do this because, seriously, if you do it, I know it takes you about like 10 seconds extra to start with. If you start with it, you'll never get problems wrong because you'll always know what you have to start with, you'll know your units, and you'll know what you're looking for. And that's really all I care about. I don't want to read that question any more times than I have to. I'll read it one time to all the information I want. So, question. So I call these the givens or the knowns. You can call it whatever you want. At 700 millimeters of mercury, a sample of hydrogen. Is that hydrogen? No. H2. Think of our diatomic gases. All right, a sample of hydrogen has a volume. Ooh, I even know it's a volume, so I'm going to say V equals, so volume equals 500 milliliters. What was this first one labeled? So I would put P out here. Pressure. Okay. All right, so I read the first sentence, I'm not reading it again. If the pressure is decreased to, so my pressure is decreased to 538 millimeters of mercury, what will the new volume be? So as I'm reading, I'm writing down the things that I'm saying to myself. Now, I'm not going to read the question again. I'm going to look at the data in my hand and figure out what can I do with this. So step 1 is where I always write down your givens. Step 2, is there a law you can use? A gas law? Why boils?
Because you only have to do the pressure and volume.
Pressure and volume twice, right?
Yeah.
So you have to figure out, I've got a P, a V, a P, and an unknown V. So then you go, oh, well, I only have one rule or one law that I can use. P1, V1 equals P2, V2. Let's go ahead and label who's 1 and who's 2 here. The rule is, if you have things that are said together, they're probably from the same scenario, so they're both labeled the same number. So if this was 700 millimeters mercury, that's P1, and that had a volume of 500, that's V1. So then the second set of information given to me was P2 and then V2. Okay. So after you have your knowns, you find your law. Third thing to do is to set up variables before you plug in, because the one thing people mess up is they try to solve it right now, when all you got to do is rearrange your variables first and then plug your information in. Because if you plug it in now, you can easily mess up a number. The less numbers you hit on your calculator, the less mistakes you make. So let's set it up according to the variables. So P1, V1 equals P2, V2. What am I solving for? How do I solve for V2? Divide by P2, right? Okay, so this is what I mean. Draw it out like this first. Cancel out P2 on that side. So then you go, okay, P1, V1 over P2 equals V2. Set it up. Now I can plug it in. One thing I want to make sure, though, is that my pressure units are the same units. Are they? Yeah. I got millimeters mercury. I'm awesome. Good. I don't have to change anything. So P1 is 700 mmHg. V1 is 500 milliliters. P2 is 538 millimeters mercury. So I can solve now, but let's double check our units cancel. What units can cancel? Okay, millimeters mercury gone. Milliliters are left. Is that a unit of volume?
Yes.
Definitely. So always double check your units, match what the heck you're looking for, because if not, you've messed up something. You've put something in the wrong place.
So you don't have to convert it to milliliters?
Nope. Because this is units of pressure units that I've canceled out. Milliliters is a unit of volume, so we're in good shape because that is qualifiable. All right, will someone do that for me real fast? B2 is what? 650.6 milliliters. So 651 sig figs. Okay, let's make sure that makes sense. So my fourth step is always, does that make sense? Take your box of air. What did I do to my pressure? Decrease it. Come on, you can do it. Decrease your pressure. Put less pressure on your box. It should expand, right? Does your volume get bigger?
Yes.
Yes, it goes from 500 to 650. Good job, makes sense. So step 1, given. Step 2, what's the law? Step 3, rearrange the law. Step 4, does it make sense? Okay? Okay, pull out your problem sets. I've got 16 examples. They're laid out per law. I'm sorry, it's not your problem set. It's your lecture notes. I copied them off. Yes, do it on the steps you get, but you're going to turn it into me. Okay, so right next to all your graphs, it says honors chemistry lecture notes 14 gases 1 through 16. I want you to do at least one in each group before you leave, but we're not done yet. I've got one more set of intelligence for you, so work on this for about 20 minutes. If you work hard, then you probably get over half of them done. I'll do some examples with you if you want me to. Let me know. We went over them earlier, but you might want to get the other gas laws. So no, you do not go to number 1 again. I just did number 1.
Okay, number 2. At 8 a.m. That's not very well.
This is volume.
Oh, God.
We know those lines.
Theory. Not a law. It's not accepted. Not exactly. So law of gravity, what is it?
When things go up, they come down.
Stuff falls, right? It's simple. So stuff falls is due to gravity. That's a short explanation. What is a theory in contrast? No, not talking about gravity. It's a what? Very detailed explanation of what I have seen in the lab, what I have seen in research, what I've seen in international research across all countries. So the theory of evolution is a book, people. It is huge. So it's very, very detailed to support all the evidence that you've gone through and seen in certain experiences. We also have theories in chemistry because we've seen all these things happen, and we have to come up with something that says, yeah, like if we increase temperature, the volume should increase. And that's called a gas law, but it came from all the experiences we've seen in the lab. So we classify it as the kinetic molecular theory of gases because it's talking about molecules, it's talking about kinetic energy, which is directly related to temperature, and it's talking about gases. So there's these 5 statements that I call postulates. They're called postulates, which just means statements about ideal gases. Well, okay, who in here is my ideal student? Okay, I have a couple of ideal students. All right, so there are people who do their homework, and they come to class right for their warm-up, and they're excited to see my demos, and then they email me questions, and they make sure that they know what they're doing. They show all their work. They're ready for the test. I mean, just all that stuff, right? Okay, so girls, what's your ideal guy like?
Oh.
Pretty much strong. What else? Facial hair?
No.
Facial hair, okay. All right, let me tell you about my ideal guy. So he makes my coffee for me in the morning. I do not like to get up and make my coffee. I want it to be made. Okay. He helps me cook with cookies. I'm a good baker. Cooking's not really my thing. Crock pot, we're like best friends. Yeah. He'll go running or walking with me and my puppy. He used to help me grade papers when it was multiple choice, and now he's like, I can't touch that. Yeah, so I've got, all these features about ideal people. Well, ideal gases are the same thing. There's all these special characteristics. They're just like, oh, yes, if you can act like that, you would be a perfect gas. So, ideal gases, if they have no volume, there's essentially negligible volume, that would be an ideal gas. Because the reason why we have to know what the ideal gas characteristics are is because if we can assume that, we get one equation to work with, and our life is easy peasy. If we don't assume these specific quantities and these specific characteristics, we got to use this big, huge equation that's really complicated. So if I can tell you a gas is ideal and you believe me, you could use the easy formula. If you don't believe me, you can go teach yourself the hard formula. So that's what we want to talk about this, so you know the characteristics of these when I talk about them. So essentially they have no volume. The gas particles are in constant random motion. They're sporadic, moving around quite a bit. They have elastic collisions. No kinetic energy is lost. So they actually hit each other and then bounce right back. Nothing is lost. Kinetic energy is proportional to Kelvin temperature. And so you can just put like IG, ideal gas all the way through, right? Last one, they do not attract or repel. So that means they don't have what three-letter thing we talked about earlier? IMFs, right. So they have no IMFs. So that's what our ideal gases would act like. They don't hang out with their friends. They're constantly roaming around. They don't like get attracted to their neighboring particle. They have very, very, very little volume, so the volume that we say is in the container is the whole of your volume that they can take up. That just helps us with our calculations. So, but really, people, is there such thing as an ideal student or an ideal person? Yeah. No. Yeah. Ideal gases, do you really think that everything acts exactly like that? No. Yeah. In La La Land, maybe, Stevie, you sure. But no. This is what we assume because it helps us with calculations because we don't want to do the hard work. Really, real gases, guess what? Opposite of ideal. So what do you think? First statement here. They have volume, okay? Ideal gases are in constant motion. Real gases they do move, but they can be not so random. You know how things can attract to one another? Like two water particles can attract to one another. They can hang out and be friends and they can move around together. So it's not so random because they're actually sticking to one another. They're cohesive or adhesive. Real gases have elastic collisions, so we're going to say non-elastic. If it's not elastic, then they actually lose a little bit of energy every time they collide. I don't know what's going on here. So a little kinetic energy is lost as they collide. And so if things collide really harshly with the sides of a container, and you were holding that container, what do you think it would feel like? Can you feel the particles bouncing off your hands? No. What if they're bouncing really hard? It gets hot. Thank you. It gets hot because the kinetic energy is being transferred to wherever it's hitting, and that energy is transferring as heat to your hands. So you actually have felt that before, like whoever touched the hood of your car after you're done driving. Well, there's pistons in there that are pushing gas together, releasing gas, pushing gas, releasing gas, and all that stuff together. The gases are moving around and colliding very viciously. It warms up your engine, amongst other things, but that's just one factor. Yeah.
So does that feel like it can lose all of its energy?
Probably not all of it, because there's still ambient room temperature that's giving it and feeding it energy, but not all of it. Technically in a vacuum, yeah. Okay, ideal, this is true for everything. Kinetic energy is proportional to Kelvin in both real and ideal gases. And then they do not attract or repel. What do you think for real?
They do.
They do. IMFs are in action. They're in real gases. That's not reading good. Real gases. So ideally, we have to assume those 5 characteristics are true because it really helps us with the next rule or law I'm going to show you here. It's called the ideal gas law. Huh? Guess what? Refers to ideal gases. Kind of makes sense. Can I go forward? Almost? Okay. And I call this the KMT. So anytime you see the thing KMT, it's not like CMT, it's KMT. So kinetic molecular theory. Okay. This is one image that you'll see a lot, and it's a graph representing gases under different conditions. So if this dashed line right here represents ideality or an ideal gas, the closer you are to that dashed line, the more ideal you act. Would you say at high pressure or low pressure things are more ideal? Why? Which side of the graph, left or right? Left, because over here, everything is much closer to that dashed line than way up here. So low pressure is ideal. How about temperature? Oh, temperature is not really listed very well here. Yeah, so let's not do Okay, so low pressure, take your box of air. Box of air, give me some low pressure. Okay, what are the gas particles doing? Spreading out. Do they feel each other? Not really. Are they interacting?
Yeah.
Are they randomly moving?
Yes.
Yes, they're randomly moving. No, they should not be interacting. They got all this space. It's like 40 million acres. They can go do whatever they want to. They don't hang out with anybody. They don't have any intermolecular forces. So low pressure is an ideal situation. And if you okay, so if I'm running by Sean and I'm a gas particle and I'm slow, I can easily become attracted to an IMF here. But what if I'm super fast? Okay, I don't have time to interact, right? Set speed, I know, it's light. So, if I was a fast-moving particle, I would not interact very well because I'm just zooming by the other particles. So, that would make me satisfy the ideal gas rules, right? Right. Higher the temperature, the more ideal, because there's no time for IMFs. There's no time or ability for the things to interact because they're moving so speedily past each other. So, low pressure, high temperature means that you approach ideal gas behavior. IGB, ideal gas behavior. So, opposite of that would be high pressure and low temperature. What would you be approaching? Real gas behavior. So, give me a box of air whenever you get a chance. Give me some high pressure and really slow moving particles. Okay, and then you're so squished close to each other, and then you feel the attractions because you're moving really slow. All the odds are against you. You have no choice but to interact because you're here, you got to get into that little big box. Okay, so that's the graph that correlates. Oops, I just did a. Oh, you okay? Yeah. Something's okay. All right. This is what I want to get to. I got time. Okay. This is the last bit on the KMT, the kinetic molecular theory. This is the writing intensive part. Sorry. You'll have to be able to tell me why the KMT is important. Now, the reason it's important is because gases have really low density, right? They're floating on top of us. They are not sinking to the bottom most of the time. So low density tells us that grams per liter, we have little mass per volume. It helps to explain that because they're able to expand and not interact, and then they can sporadically move around. And then we all know we can compress a gas, right? We've been doing that all day. We've been squishing our box of air. The reason you can do that is because how far apart are gas molecules, do you think? On a normal day. Really far, right? So here's one here, and here's one here, and here's one here. All that space in between is just emptiness. So compression is you're able to do that because there's so much space you can actually shove them closer to one another. Expansion's the same way, you're just going the opposite way. So that helps us to explain that one as well. Diffusion, so, we talked about volatile, deodorant, and body spray. If I had a lot of body spray, Jake would smell it first. Her skin too much today. And then maybe Kevin. And then maybe Jessica, in about 5 minutes. Dang, she's got so much. Right? It's insane. So the reason that happens is because what's happening to the particles from me to you? They're moving from what, Cameron? Right, high concentration me to low concentration you. So they're diffusing because they're sporadically moving around, not interact with each other. So that's our diffusion. Diffusion is through a small hole. So like a balloon. They don't last forever, right? They don't last forever, unfortunately. Why? What's happening? It's leaking through what? A small hole. So a balloon can leak through a small hole, and gases can move through it. So we're going to talk about how those big carbon dioxide molecules, they move really slow, but helium moves really fast. So which balloon did I prefer? Why? I get to keep it for weeks versus 2 days. Right? I don't care if it floats. I can tape it to the wall. Let's make it look like it floats. I want to make it last. All right. This is the ideal gas law. It's called PV equals nRT. And this is the last thing. I think I have one example for you. So you can know these. PV equals nRT. if you got your 5 simple ones, and this is the one that kind of has very, very, very specific units, you don't get to choose your units. You've got to convert to the units I give you. I want you to always put pressure. Let's write that first, actually.
Remember KMT, but what does it like stand for?
Kinetic molecular theory. So previously in Boyle's law, you could put pressure in atmospheres and torrs, kilopascals, bars, what was the other ones? Torr, millimeters of mercury. You can put in any pressure you want, as long as P1 and P2 are the same unit. Now we have no choice. You see this universal gas law constant? It's called R. It's got 4 units in it that must be the same in the other variables that you are using. So 0.0821 is the number associated with the constant. Atmospheres, since it has atmospheres in it, our pressure has to be in atmospheres before we use this equation. Since it has liters in it, guess what? Which of these will have to be liters? Volume. The volume has to be in liters. No milliliters, you got to convert to liters now. This moles, well, yep, count in moles. We're not going to put mass in there, we're going to put moles. And then Kelvin is going to be our temperature unit. So now we're getting kind of specific, and we're going, yep, you've got to convert pressure to the correct unit. And that's just because for ideal gases, you get to use this nice equation because it's one simple equation for anything that I tell you is an ideal gas. It's just we all got to talk about it in the same terms, so we have to talk about all in the same units. So let's say, for example, I said, so it's my birthday, and I got a balloon, and I wanted to put in my balloon 4 moles of helium. And my 4 moles of helium, they're going to bounce around on the inside of the balloon. The balloon's purple, and my birthday's not actually tomorrow, it's like November. And give me all this other miscellaneous information, right? But I'm going to be on top of Mount Everest, so give me a pressure that I could say. On top of Mount Everest. Huh? 0.01. 0.01 what? 0.01 atmosphere, so I'm on top of Mount Everest. And I'm just, piddling around, I'm playing with rocks and stuff. And it's really cold. It's real cold. Negative 70 Kelvin. I like it. Okay. But I want to know how big my balloon is now. It's negative 70 Kelvin. Oh no. Okay. Well, that is pretty low. Okay. Positive 70 Kelvin. All right. So how big is my balloon? How are you gonna do it? What am I asking when I say how big is my balloon? I'm asking for the volume of my balloon.
So you do 0.01 times.
Okay. Fine. First thing, we labeled our constant, or all of our variables, right? This is our N, this is our P, this is our T, and this is our L, okay? So that's done. Let's rearrange the variables first, and then we'll plug them in, okay? So some of you guys are good, but I want to make sure we're all good. So PV equals nRT is my formula. What am I solving for? Question. I'm looking for volume. So what am I doing? Dividing by pressure, dividing by pressure. So volume is equal to nRT over P. All right, now let's plug it in. What was my N value? 4 moles of helium, right? So 4 moles. What's my R value? Okay, and I'm going to write this out so that you can see how I write it and how we're going to cancel the units together here. If I can move this. Oop, just move those P's on accident. Oh, nope, that's not what I want to do. Okay, let's pretend those P's aren't there. They're just hanging out together. Okay, so 0.0821 atmosphere liters per mole K. That is a one big humongous unit. You've got to write it. And then lastly, temperature is 70 Kelvin. And the entire denominator, so I have like a unit, like a fraction on the top here. The pressure down here is 0.01 atmospheres. What units can cancel, top and bottom? You see moles here in this numerator? So what if I draw a line up here as a whole? Okay. Moles on top here, moles on bottom here. Yes? Cancel. Kelvin on top here, Kelvin on bottom here. Cancel. Liters? No, they don't cancel, and that makes sense because this has to be in liters. Okay? And then atmospheres on top, atmospheres all the way on the bottom. Alright, so all those units cancel, leaving us with liters. Yay, will someone calculate? I got my phone, or my other stuff here. I want to see the volume of my little bitty balloon. So in your calculator, you're going to put 4 times 0.0821 times 70, enter. So that's top number is 22.988 some unit liters. And then divided by 0.01. Holy cow. Volume of helium balloon is, anybody? 2,298.8 liters. That's because, why does that make sense?
And there's only
Well, it's not because of the super cold, it's because of the pressure. Take my pressure and I go way out. It expands so much and it makes it that big. Why do you need the temperature? Because different pressures are affected by different temperatures differently. Remember PT? You gotta move that. Alright, yeah. I just randomly, I told you I have 4 moles of air in my balloon. I just told you that in my little goofy story. It would say it in the problem though. Yeah. Alright, so do me a favor. You've got 4 minutes. You can get at least 2 more problems done. Don't you pack up.